Hello everyone, welcome to the course on signal system. This is lecture 1 and in this lecture we will see the basics of Laplace transform. So we have seen various type of transform used in signal system. So some of the transforms are applicable for the continuous time system, some are for discrete time system. So in the today's lecture we will see that how this Laplace transform is helpful to analyze the continuous time LTI system. So first of all, what are the motivations behind to study the Laplace transform? So first is, it is a mathematical tool by which we can study various type of signals and systems. The Laplace transform, we'll see later on that what is the relationship between the Fourier transform and the Laplace transform. So here at this stage we are saying that the Laplace transform is a generalized case of Fourier transform. So due to its more general nature, the Laplace transform has numerous number of advantages over the Fourier transform technique. Next, the first advantage is the Laplace transform representation exists for some signals that doesn't have their corresponding Fourier transforms. So due to this particular advantage, we can see that the Laplace transform can handle a larger class of signals with this particular transform. Second advantage is the Laplace transform is a more general tool, so it can provide additional insight beyond those facilitated by the Fourier transform technique. So next is the relationship, how we can basically calculate the Laplace transform for any LTI system. So let's say if H is the impulse response, if capital, we have seen that the LTI system can be represented by its impulse response, which is given as H of t. So this H, small h letter, that is in the time domain, whereas the capital letter, which is corresponding to the Laplace transform of Ht, which is H of s. So capital I am using here for the transform and small letter is used for the time domain representation. So if we have the impulse response of a LTI system represented by Ht, so the Laplace transform can be evaluated with the help of this relationship H of s equals to minus infinite to infinite Ht e raised to power minus St dt. So in this way we'll be having the corresponding, so this H of s can be also be referred as the transfer function. So in the next lectures we will see that how we can solve the differential equation. So we'll see the definition also, the transfer function. It's a ratio of Laplace transform of output to the Laplace transform of input with zero input conditions. So now since the Laplace transform has already appeared earlier in the context of LTI system, it is very important tool. Furthermore, we'll see that Laplace transform are having many additional uses also, like to solve the circuit problems. If we want to solve some control system problem also, then we can use this particular tool, Laplace transform. So these are the motivations behind the Laplace transform. Now we'll discuss further that what is the bilateral and the unilateral Laplace transform. So as the name bilateral means that it is a more generalized form of Laplace transform. So if xt is a signal, if xt is a function in the time domain, so L here is corresponding to Laplace. So if you want to calculate the Laplace of the time domain signal x, so we are representing by a capital letter which is capital of X, and the relationship we can see here with the help of equation number 1, that x of s equals to minus infinite to infinite x of t e raised to power minus st dt. Whereas we are having one more relationship which will basically calculate the inverse Laplace transform. Means if we want to solve the time domain signal xt with the help of given Laplace transform, so we can utilize the equation number 2. So the generalized form is xt equal to 1 by 2 pi j. The limits are sigma minus j infinite to sigma plus j infinite x as e raised to power st ds. So this is the equation we use to basically calculate the inverse transform, but we have some other method also. In the next classes we'll see. So where real part of S, sigma, we are aware in the complex S plane, in the complex S plane, we can say we have sigma is a real part, j omega is the imaginary part. So if real part of S we are talking about, then we must be clear that we are talking about sigma, and if I am talking about the imaginary part, so it is nothing but j omega. Now most of the time we'll refer that xt, this interchangeable sign, that its transform, Laplace transform is x of s, and naturally the inverse transform is x of t. So as I was telling you that generally we don't use this equation number 2 to calculate the inverse Laplace transform. We have some other methods like partial fraction technique. So we'll see, we'll discuss later on that how we'll utilize this partial, we'll use this particular technique to solve the inverse Laplace transform. So bilateral here means we have the limits from minus infinite to infinite, means both the sides. Now we'll see what are the differences between the bilateral and the unilateral Laplace transform. So more or less we are talking about two different versions of Laplace transform. First is bilateral. Bi means two-sided, whereas unilateral means only one-sided. So if it is both-sided, that means the limits of the integration we are talking about, they are from minus infinite to infinite, whereas in unilateral we can say it may be from 0 to infinite. Or next is the unilateral Laplace transform is most frequently used to solve, very important, to solve the linear differential equations with non-zero initial conditions. Means if the initial conditions are non-zero, then we will see that we can use this unilateral Laplace transform to solve these type of equations. So the only difference between the definitions of both the transform, which is bilateral and unilateral, is in the lower limit of the integration. So in the bilateral, as we have seen, the lower limit is minus infinite and the upper limit was infinite. In unilateral, we have the lower limit set to 0, whereas the upper limit remains same. So for the most part, we will focus our attention primarily on the bilateral Laplace transform. Most of the time we are using the bilateral Laplace transform. However, we will see that unilateral Laplace transform is a tool for solving the differential equations. Next, so we'll see that all subsequent references to the Laplace transform should be understood by means of bilateral Laplace transform. So after this, we have seen that how this bilateral is different from unilateral. Next, we want to see that what is the relationship between the Laplace transform and the Fourier transform, because as we all are aware that Fourier transform is a special case of Laplace transform. So if we can see that in the S plane, complex X plane, we have S equal to sigma plus j omega, where sigma is a real part and j omega is a imaginary part. So what we have studied in Fourier transform, that if sigma equal to 0, if sigma equal to 0, that means we are doing calculations on, we are calculating on j omega axis. So that's why we just said that Fourier transform is a special case of Laplace transform evaluated over the j omega axis. So let's say if we have x and xf denote the Laplace transform and CTFT. x is the Laplace transform, x of f is the CTFT of the time domain signal x. So the function x of s means the Laplace transform can be evaluated by putting s equal to j omega, where omega is real yields, it will give you the Fourier transform. So that means we have seen that if the real part of s, which is called as sigma, if it is 0, that means we are having a Fourier transform. So the Laplace transform and the Fourier transform both are equal if the real part of s equal to 0. So due to this particular relationship, the Fourier transform of x is sometime written as x of j omega x, x of j omega also. The function x of s evaluated at an arbitrarily complex value s, which is sigma plus j omega, where sigma is the real part and omega is the imaginary part, can also be expressed in terms of Fourier transform which involve the x. So if we can see that if we have the equation, generalized equation of Laplace transform, x of s equals to minus infinite to infinite xt e raised to power minus st dt, and if we substitute s equal to sigma plus j omega, then we can see that minus infinite to infinite xt e raised to power minus of sigma t and e raised to power minus j omega t and dt. So if we can clearly see that this whole quantity xt e raised to power minus sigma t, so we can correlate that Laplace transform is nothing but the Fourier transform, continuous time Fourier transform of this whole signal, which is xt e raised to power minus sigma t. So in general, the Laplace transform of x is a Fourier transform of an exponentially weighted version of x. This is quite important. So due to this weighting, we can say that the Laplace transform of a signal may exist when the Fourier transform of the same signal does not exist. That means we can say that Laplace transform is more generalized form of transform. So that's why we are going to study. So these are some motivations behind the Laplace transform. Now we'll start with the first example. To find the Laplace transform of the function where we have a as a constant and the signal xt or the function xt is e raised to power minus at ut. So from the definition of Laplace transform, we can say that x of s equals to minus infinite to infinite, we have e raised to a minus at ut e raised to a minus st dt. Now because of ut, we are already aware that ut, the value is 1 for all t greater than equal to 0 and the value is 0 for all t less than 0. That means due to which the limits of the integration will be changed and now they are becoming from 0 to infinite e raised to power minus of s plus at, we are combining exponential terms dt, whereas the integration is minus 1 by s plus a and e raised to power minus s plus at, whereas the limits are from 0 to infinite. Now what we can say that in order to more easily determine when the above expression converges, means we are calculating x of s. So what are the conditions for which this transform converges? We can clearly see here also, if we can expand this equation 0 to infinite e raised to power minus of sigma plus j omega t and e raised to power minus at and dt. So if we just combine the real part and the imaginary part, this is 0 to infinite e raised to power minus of sigma plus a t and e raised to power minus j omega t and dt. So clearly, if I'll ask that what is the condition for which this particular transform converges? So the answer must be that once this quantity sigma plus j omega quantity or sigma plus a basically, if this quantity is greater than 0, means some exponential curve of this type, when let's say this is of e raised to power minus 2t type, exponentially decaying type, means sigma plus a must be greater than equal to 0. So this is a condition for which the transform x of s will converge. So we can see in the another way that in order to move more easily determine when the above expression converges to a finite value, we substitute s equal to sigma plus j omega, as we also substitute here. So instead, in this particular equation number 1, we'll put s equal to sigma plus j omega, and we just solve this. And now how when this x of s converges, so we have seen that once sigma plus a is greater than 0, the above expression x of s converges. So which can be further simplified as we are aware that sigma is nothing but the real part of s. So real part of s must be greater than some constant which is minus of a. So if this is a scenario, then we can say that x of s equal to 1 by s. So this is the final result we are getting, x of s equal to 1 by s plus a. So the result is e raised to power minus 80 ut, the Laplace transform is 1 by s plus a, with the condition that real part of s greater than minus a. Now this condition, real part of s greater than minus a, this is nothing but the ROC, which is called as a region of convergence. So region of convergence, later on we will see the definition also. So region of convergence is basically, it's an area for which it is the region of real part of a for which the Laplace transform of any signal xt converges. So we have basically the condition real part of s greater than minus a. So first scenario is, if we can see this region, this shaded region, first case is this, second case is like this. So the first case will arise when a is a positive quantity, means when a is greater than 0, so the entire region will be shaded, and this region is called as the region of convergence, means for all those values of real part of s greater than minus a, the Laplace transform x of s converges. That's the definition. Similarly, we have the second figure over here, which says that if a is a negative quantity, so if a is a negative quantity, automatically this will become positive and the region will be this one to the right. So again, we have the real part of s, which is sigma, is greater than minus of a. So this basically, this region basically known as a region of convergence, and we have already seen the definition of region of convergence. Next is, find the Laplace transform of function where we have xt equal to minus of e raised to power minus at u of minus t. So again, we'll initiate the transform with the help of the generalized expression for Laplace transform, minus infinite to infinite xt e raised to power minus st and dt. But we can clearly see that because of u of minus t, the limits of the integration are going to change, and they will be from minus infinite to 0 only now, and minus of e raised to minus at e raised to minus st dt. Further, if we'll further integrate this, we are getting 1 by s plus a, and further the limits are from minus infinite to 0. So now if I'll ask a small question, that if we have the Laplace transform x of s and we want this Laplace transform to converge, so how we can see? Minus infinite to 0 means the time is negative over here, and we have the minus sign we can take outside, which is nothing but the magnitude, which is nothing but the sign, the amplitude basically, e raised to a minus sigma plus a this side n e raised to the power minus j omega t and dt. We can write something like this. Now, here we have t also, e raised to the minus sigma plus a t. Now, we want this transform to converge. So, we want this transform to converge, but t is a negative quantity. So, overall this is negative. So, if we'll say that sigma plus a is greater than 0, so definitely it's not going to converge for any value of sigma. But if we will see that sigma plus a, if this value is negative value, means if sigma plus a is less than 0, then definitely we can visualize that this is negative, this quantity is negative, and t is negative, and this is negative. So overall we have negative quantity. So that means we can say that if sigma plus a is less than 0, which is real part of s is less than minus a, then we can say that the Laplace transform x of s converges, and once the Laplace transform converges, so definitely we are able to calculate the transform. So x of s equal to 1 by s plus a. So clearly if you'll see that both our previous example, which is e raised to power minus at ut and minus of e raised to power minus at u of minus t, both leads to the same type of result, 1 by s plus a. But clearly we can see that this first one is a right-sided signal because of ut, and this second one is a left-sided signal because of u of minus t. But the transform for both the functions, whether it is a left-sided or the right-sided, the transforms are same. So how to distinguish between these two functions? So the answer is we can distinguish these functions on the basis of their ROC. So if we can write down the complete answer, so the transform is 1 by s plus a, whereas the real part of s is greater than minus a, whereas here we have seen that real part of s is less than minus a. Now the result is complete. The results are same, but the region of convergence for both the transform are different. So now for the second one, which is e raised to power minus of at u of minus t, if we will plot the ROC, if we will plot the real part of s, which is nothing but sigma, so we can say that it is less than minus a. So the region will be, entire region to the left of minus a will be considered as the part of ROC. Means any value which lies between this minus infinite to minus a will converge the Laplace transform x of s. Similarly, we have the second picture. So the first picture says that when a is a positive quantity, definitely when a is negative, then this region, this point will be shifted in the right hand side, and the region again will be having the left, to the left of minus a. Means again for those values of real part of s or sigma for which the Laplace transform of xt converges. So after this we can start with the third problem, which is the Laplace transform of a unit step signal or the unit step function. So for the unit step function x of s, we are having minus infinite to infinite ut e raised to a minus st and dt. So because of ut, again the limits are from 0 to infinite, e raised to a minus st dt. So minus of 1 by s e raised to a minus sigma t and e raised to a minus st, whereas the integration limits are from 0 to infinite. Again we can see that here 0 to infinite, instead of s I can write sigma plus j omega t and dt. If we can simplify, 0 to infinite e raised to power minus of sigma t and e raised to power minus j omega t and dt. So if we want the Laplace transform x of s to converge, that means the quantity e raised to power minus sigma t has to converge. So when this will converge, we'll be having the value of sigma greater than 0, or we can say the real part of s is greater than 0. So for real part of s or sigma greater than 0, the transform of ut will definitely converge, and that's why we are getting a result x of s equal to 1 by s. So here we have the complete answer that ut equal to 1 by s for all real part of s greater than 0. So after this, we have the last definition. In the next lecture we will see that what is region of convergence. Before that, we have to define that let R denotes a set in the complex plane. So a set R comprised of the complex number s such that real part of s less than a, as we have seen that less than a means we are having the left hand side of s plane. In s plane we have left hand side. So again we have two cases, when a is positive, when a is negative. So this is when a greater than 0, this is the case when a less than 0. Similarly, when the real part of s is greater than a, again, so this will give rise to the plane which lies to the right hand side of s plane. So for some real constant a is said to be the right half plane, RHP. So again we have two cases, one for a greater than 0 and the other case we can see this is for a less than 0. Both the figure shows that the region of convergence is to the right of the pole. We'll see later on some properties of the region of convergence, ROC. So definitely for right sided signal and for left sided signal, we are going to decide that what is the region of convergence for the Laplace transform x of s. So this is all about the region of convergence. So in our next lecture, we will see that there are some 7 to 8 properties which are definitely helpful in deciding that what is the corresponding region of convergence for x of s. So these are the references. Thank you.